All right, in this video I'm going to go over section 10.2, which is all about properties of power series. In the first couple examples I'm going to show you how to find the interval of convergence and the radius of a convergence using the ratio test. In the last couple examples I'll show you how to construct new power series from old power series. Okay, so first let's look at this series right here. It's a series from k equals 0 to infinity of k times x minus 1 to the k. So just so if you look at this, you can see that the coefficients of the power series are just k, and this thing is centered at a equals 1. So to find the interval of convergence, we always use the ratio test. So we first start out with, in the ratio test, assume this thing is the a sub k. So I would do the limit as k goes to infinity of the absolute value of a sub k plus 1 times the reciprocal of the expression 1 over a sub k. So plugging that in, I get the limit as k goes to infinity of k plus 1 times x minus 1 to the k plus 1. And then I would be dividing by k times x minus 1 to the k. So this is what I would have here. Simplify this a little bit. So there's only x minus 1, there's one x minus 1 left in the top. I would have a k plus 1 over k, and the absolute value of that. So the only thing here that really has a different sign is x. K plus 1 and k are always positive, so I'm left with k plus 1 over k times the absolute value of x minus 1. I can factor out through the limit the expression x minus 1 because it doesn't depend on k. And then I want to take the limit as k goes to infinity of k plus 1 over k. So this limit right here, right, is equal to 1. So when I do this limit as k goes to infinity of a sub k plus 1 over a sub k, I literally just get the absolute value of x minus 1. So in order for this thing to converge, we know that x minus 1 absolute value must be less than 1. So when it's in this form right here, the interval, I can pick out this number on the right hand side. That's the radius of convergence. So we know r is equal to 1. However, continuing with this inequality, I can set x minus 1 less than 1 and greater than negative 1. And finally, I get adding 1 to both sides. X is between 0 and 2. So right now, this is my interval of convergence. But I do still have to check the endpoints. Because the ratio test is not conclusive there. It's inconclusive. So plugging in x equals 0 into my series, I see that I will get the series k equals 0 to infinity of k times 0 minus 1 to the k. So I get the alternating series k equals 0 to infinity of negative 1 to the k times k. When x equals 2, I would get the series k times 2 minus 1 to the k, which would be not an alternating series in this case. It would just be the series k. Right? Because 2 minus 1 is 1, 1 to the k is 1. This thing diverges by the divergence test. Why? Because the terms go to infinity, which is not equal to 0. Therefore, x cannot equal 2. Finally, this one also diverges by the divergence test. Why? Because the limit as k goes to infinity of negative 1 to the k times k, that essentially approaches plus or minus infinity, which is not 0. So x also cannot be 0. So this is, in fact, I'll stop here. This is, in fact, my interval of convergence, not inclusive on both. And my radius of convergence is 1. So this series only converges for x inside the interval 0 to 2. Okay, so that's how you show the interval of convergence. Make sure you check the endpoints at the end of the day. Let's try another one. This one's really tricky. So exact same method, ratio test. So I do the limit as k goes to infinity of the absolute value of a sub k plus 1 times 1 over a sub k. Now, in this series, the terms are 1 over k to the k. And the center is 0 because I'm not actually subtracting anything off. So putting in k plus 1, I would get x to the k plus 1 over k plus 1 to the k plus 1 times k to the k over x to the k. So looking at this, we get the limit as k goes to infinity. We would be left with an x up top times k to the k all over k plus 1 to the k plus 1. Again, everything here is positive except the x. That could be negative, so that's the only thing that gets the absolute value. I'll write the top as k to the k, and I'll write the bottom as k plus 1 to the k times k plus 1. Now, this is a little tricky, but I have absolute value of x. I have a k over k plus 1 all to the k times 1 over k plus 1. I can write it like this. Factor out the x. Also, I'm going to rewrite this guy to look like the following. I can write this as 1 over k plus 1 over k to the k, and this is 1 over k plus 1. So here I got the limit as k goes to infinity. Now, look, I can write this as 1 to the k, which is just 1, and this is k plus 1 over k to the k, all times 1 over k plus 1. So here I have limit as k goes to infinity. This is the same as 1 over 1 plus 1 over k to the k times 1 over k plus 1. Now, this thing right here, I'm going to box it, this thing, that it goes to e as k goes to infinity. This thing, if I box this, this goes to 0. So, at the end of the day, after I evaluate the limit, I would get 1 over e times 0, which is 0 for all x. Therefore, my interval of convergence, x can be negative infinity to infinity. In other words, this thing converges for all x. Okay. So that is one that is kind of like a best case scenario. Right? It doesn't matter what x is, this thing will always converge. All right, this one's kind of crazy as well, but exact same method. If I want to find the interval of convergence, I do the ratio test. I do the limit as k goes to infinity of a sub k plus 1, right, times 1 over a sub k, which is equal to the limit as k goes to infinity. So I would have negative 2 to the k plus 1 times x plus 3 to the k plus 1 all over 3 to the k plus 2 times 3 to the k plus 1 over negative 2 to the k times x plus 3 to the k. A lot of stuff cancels out. We see that we only have a negative 2 in the top. We only have an x plus 3 in the top. And we only have a 3 in the bottom. So when I do this, notice that I would get the limit as k goes to infinity of 2/3 times the absolute value of x plus 3. Since nothing now depends on k, that's exactly what I'm left with. And so for this thing to be convergent, we know that 2/3 times x plus 3 must be less than 1. Working with this, this interval here, I'll multiply by 3/2. So x plus 3 must be less than 3 over 2. And so right now, once I get it in this form where the absolute value of something is less than something else, so I know my radius of convergence is 3/2. Okay, so if I continue working with this thing, I can write it as x plus 3 is less than 3/2 and greater than negative 3/2. All right, so now I just subtract 3 on either side. 3 is the same as 6 over 2, so this would be negative 9/2 is less than x is less than negative 3/2. So this right now is my interval of convergence until I check the endpoints. So again, this test is inconclusive at the endpoint, so I have to check them separately. So I like to first plug the endpoints into the original series to both of them, and then I'll determine if each series converges or diverges. So I would have negative 9 over 2 plus 3 to the k all over 3 to the k plus 1. So simplifying this, negative 9 halves plus 3, that would be negative 3 halves. Notice that this is equivalent to 1/3. I'm going to pull off one of the 3's in the bottom. And then overall, I'm going to have a negative 2 times negative 3 halves, which is positive 3 divided by 3. I get 1 to the k. So this is the same series as k equals 0 to infinity of 1/3. And this diverges by divergence test, because 1 over 3 as k goes to infinity will not go to 0. Okay, finally, if I plug in negative 3 halves, and I just want to make a note here, this will always occur for our purposes anyway. I should get the same exact series but alternating. So I would get negative 2 to the k times 3 halves to the k all over 3 to the k plus 1. And here we have the 2's cancel. I'm putting everything to the k. I would be left with a 1/3 out front and a negative 1 to the k. And since this thing diverges, this thing would go, so I can do the divergence test. The limit as k goes to infinity of negative 1 to the k to the 1/3. Right, that's always equal to plus or minus 1/3, which is not 0. Right, so this also diverges. So just like in the previous example, this turns out to be my interval of convergence, non-inclusive on both. So this thing converges for x inside negative 9 halves to 3 halves. Okay, so those are pretty tricky problems, but always make sure you check the endpoints. In both cases, it turns out not to happen. So kind of switching gears here, if I want to find the power series representation of another function like this one, 1 over times 1 minus x to the 4th, I can start here. The geometric series is exactly 1 over 1 minus x is the same as, it can be represented by this geometric series, right? For x less than 1. So the interval of convergence is between negative 1 and 1. There was a theorem in class that we discussed that essentially, and here I'll change the color of the marker, right? I can use this identity for a lot of different things. For example, I can change that x to be a function. So I'll write it in blue. So 1 over 1 minus f of x can actually be written as something like k equals 0 to infinity of, right, not x to the k, right, but f of x to the k. And it turns out that this thing will converge, this new function, right? The interval of convergence will be, right, f of x must be less than 1, the absolute value. Okay, so here we have exactly something like that, right? This thing, this x to the 4th, that is my f of x. Everything I just said, this f of x is different from this one, so it's not the same as that. So I'm pointing out x to the 4th. And so 1 over 1 minus x to the 4th should be equal to, right, just x to the 4th to the k. So that is the power series representation for this function. So it'll be x to the 4k. And we're done. And so, right, this has to be less than 1. This is only true, right, if x is less than 1. So the interval of convergence turns out to be exactly the same. So this one's a little bit more tricky, but let's actually, I'll show you how I can rewrite it in this term. So again, isolate this thing that's down here. So first let me rewrite this function, right? There's a 3 up top, which isn't really a big deal. But this 3 here is a big deal. So if I have 3 over, I'm going to factor out a 3 to make it a 1, which would mean that is the same as 3 over 3 times 1 plus x to the third. So I can write that as 1 over 1 plus x over 3, because the 3's canceled. Right, so I'm just kind of rewriting f to make it look like something nice. Now, I almost am done here, right? The only thing is about this pesky plus. So I could write a plus as 1 minus negative x over 3. And so now I realize, right, that look, the same theorem can be applied. This is now the f of x that I was talking about in this little identity right here. Right, so f of x, which I've just rewritten as 1 over 1 minus negative x over 3, has a power series representation, and that power series representation would be k equals 0 to infinity of negative x over 3 to the k, which can be rewritten as the alternating series, negative 1 to the k times x over 3 to the k. Right. I just pulled a negative 1 out so you could see it. So again, the interval of convergence then is negative x over 3 is less than 1. But if I apply the absolute value, I just get, right, the absolute value of x over 3, because the negative goes away, the 3 is already positive. So I get the absolute value must be less than 3. And so the interval of convergence then is this. Okay. So that's how you manipulate certain functions, and then use this identity up here to help you out. Now look, we can also work backwards. What function must be represented by this? Well, this series, write it as something to the k. I hope everyone can realize that, right? If I have x minus 2 to the k, 3 to the 2k is the same as 9 to the k. Right? Because I can apply the square first, and then raise it to the k power. So this series is the same as k equals 0 to infinity of x minus 2 over 9, all raised to the k power. And so that must be, again, I'm using the same exact identity. This is f of x, right? So this must be the function 1 over 1 minus that thing. And so that is my function, right? And I can actually simplify it. So I would have 1 over 9 minus x minus 2 over 9, so 9 over 9, sorry. And then this would be 9 over 9 minus x minus 2. So this would be 9 over 11 minus x. So that function has the following, has that power series representation. Finally, another thing we can do here is we can differentiate series to find the new power series. So again, start with this series. Start with a classic identity. I can differentiate both sides. And what's the derivative of 1 over 1 minus x? We'll use the chain rule. This will be 1 over 1 minus x squared. And so when I do the derivative of all of this stuff here, it's really just going to be k equals 0 to infinity of k times x to the k minus 1. So I just use the power rule on this function right here, x to the k, right? Bring the k down and drop the power down by 1. Again, keep in mind, I'm looking for a function, the function 1 over 1 minus x quantity cubed. So I just found a power series representation for 1 over the quantity 1 minus x squared. But I can differentiate again. So what would be the derivative of 1 over 1 minus x squared? That would be the derivative, right, of that series. I'll come up here. So what's the derivative of 1 over 1 minus x squared? Again, use the chain rule. You would get 2 over 1 minus x quantity squared. And then do the power rule here again. So I would get, so k equals 0 to infinity of k times k minus 1 times x to the k minus 2. Okay? So I'm almost there, but this pesky 2 is still here, so now all I have to do is divide by 2. And there you go. So 1 over 1 minus x quantity cubed is equal to 1/2 times this series. Now I will mention that the first two terms of this series are 0, because when I plug in k equals 0, it goes away. When I plug in 1, it goes away. So the series really starts at 2. All right, so that's just another way you can find a new series from old.